In this lesson, we're going to graph a polynomial function using transformations. We're also going to graph a polynomial function using everything that we know and everything we've learned so far about the characteristics of a graph. Graphing polynomials using transformations. So one method for graphing polynomials is that you can simply use your knowledge of transformations of graph to see whether there was a shift horizontally to the left or to the right, and you'll always know that because it's within the function itself. It's always inside. And then if you see a value outside, that will determine whether there was a reflection. If it's negative, it's a reflection about the x-axis. If it's a positive, then there is no reflection. In that case, you will have either a stretch or compression of the graph. So if that value outside is a number greater than 1, it demonstrates a vertical stretch, and if it is a fraction, it is a vertical shrinking or compression of the graph. Now, if you have a value behind the function, if it's plus some number, that means you're going to shift it up that many units. If it's minus some number in the back of a function, that means you're going to shift that function down that many units. Here's another one. We have here an even function, f of x equals x to the 4th quartic function. And what we want to do is we're going to leave the shape exactly as it is. Whenever you see a plus or minus in the back of a function, you're simply going to shift that function up or down. If it's a positive, you shift it up that many units, and if it's a negative, you shift it down that many units. So in this case, we're going to shift this function up 2 units. So our new function g of x is going to look like so. And again, it's the same graph, but just simply shift it up 2 units. Here we have a kinetic function, f of x equals x to the 5th power, and notice this time that the value is within the function, and your 5 now is here on the outside, and with x within the function you see minus 4. This indicates a horizontal shift, and everything about horizontal shifts are always opposite what it seems. So even though you may see minus 4 and think that you're going to go 4 units to the left, to the negative side, but that is not so. In fact, you're going to be shifting the graph 4 units to the right. So when we graph our new function, g of x is going to look like so. So for example, here we have a cubic function, f of x equals x cubed, and here we want to sketch that same parent function. Notice you just see here a fraction that's in front, and in addition you see a negative there too. So you're going to have there not only compression there, but you're also going to have a reflection of that graph as well. So once we sketch that graph of that function, our new function g of x is going to look like so. So the one thing about a compression of a graph is it's sort of pushing down on the graph vertically, and when you push down on the graph, it sort of makes it wider. So notice that over here that it's a little bit more room there, wider than it is on the left with the original function there, both on top and on bottom, and that's because it's compressing or pushing down on the graph. And in addition to that, we also flipped the graph, did a reflection there about the x-axis. Another strategy you can use for graphing polynomial functions is to use everything that you know so far to help you graph the polynomial function. So here are some steps we're going to take. Step 1, you can use the leading coefficient and the degree of the polynomial to determine the graphs in behavior. Step 2, go ahead and find the x-intercept, the point where it touches the x-axis. To do that, all you have to do is set the function equal to 0 and solve for x. You also want to, your next step, and again, these steps don't have to be in this particular order, but these are just simply some steps you could take. So another thing you might want to do is to look at the multiplicities of each one of the zeros, and then determine the graph behavior by that, whether at those zeros or those roots, is it going to cross, or is it going to just simply touch the x-axis? And then 4, you could also find the y-intercept if there is any. And to do that, all you have to do is to evaluate the function for 0. In other words, find f of 0, remove all the x's, replace them with 0, do the math to see what your output is. You can also use your knowledge of what you know about symmetry, graphs that are odd, graphs that are even, what they look like, whether the graph is symmetric about any axis or the origin, all of that, just using information that you know. And then also use your knowledge of turning points. Recall that the number of turning points a polynomial functions will have is n minus 1. So you can just use everything that you know to get you to the point to where you'll be able to sketch the graph or see the sketch of the graph. Okay, so step 1, let's go ahead and use the leading coefficient and the degree to determine the graphs in behavior. So in this graph, as you can see, the leading coefficient here, you can determine that because it's the one that has the highest degree. The leading coefficient is 1, that's positive. It is also a third degree polynomial, which means it's going to be an odd degree function. So let's take a look at what that will look like in terms of its behavior. We know that odd degree polynomials will have opposite ends for the direction. One will be face downward and one will face upward. In terms of how so, it's the leading coefficient that determines that. And because it's positive in this case, whenever it's a number that's greater than 0, meaning a positive, it is going to fall on the left and rise on the right. In other words, it is a graph that as you move from left to right is going to be moving in an upward motion. It's always going to end in a rise because the coefficient of the leading term is a positive. And in terms of the shape, it's going to be that S-type shape because it is an odd degree polynomial. Let's move on to the next step, use some more information that we know to help us to be able to determine what the sketch of this graph is going to look like. Let's go ahead and find the x-intercepts. Now recall the x-intercept is going to be where the graph touches the x-intercept. To do that, all you have to do is set the function equal to 0 and then simply solve for x. So actually, this is one of our problems we did earlier on the slides when we were finding the zeros of a polynomial function. And recall to do that because this particular one had 4 terms that was similar. Recall we used the 4-term factor by grouping method to solve for x. And that is, recall grouping the first group, putting those together and taking out the GCF, and doing the same for the second group. So recall with the first group, they had a GCF, a greatest common factor of x squared, and the second group, they had a -1 in common. So once we took that out, recall that our GCF is x plus 3, and what is left is x squared minus 1. Now you will need to factor that further so that you can find all of the x-intercepts, because the first factor here of x squared minus 1, that is what we call a difference of square, which factors into x plus 1, x minus 1. So therefore, we actually have 3 intercepts, or 3 points where the graph will in some way touch or cross the x-axis, and that's going to be at -1, 1, and -3. In terms of your graph, again, because it touches the x-axis, you're going to have a 0 in y's place and the x-intercept itself in x's place, because it's the x-intercept. Let's go ahead and graph those 3 points on the rectangular coordinate system. And so far, this is what we have of what a sketch of our graph is going to look like. And again, recall it's going to fall on the left and rise up on the right. We knew that from the leading coefficient and the degree of the polynomial. And now we know that it's going to touch or cross at some point and in these 3 points of -3, -1, and 1. Let's move on to step 3 to find out what else can we do to give us an even better picture of what a sketch of this graph would look like. We can use multiplicities to determine more of the graph's behavior. So we had already factored this particular polynomial up to this point, and actually we factored it even further, because recall we went ahead and factored that difference of square there of x plus 1, x minus 1. So let's go ahead and put that back. So in doing so, now that we have it completely in factored form, we can see that all of 3 of these has a multiplicity of 1. So when we add all our multiplicities together, that gives us a degree of 3, and that's right in line with the given polynomial. Out of all the degrees, the highest degree is 3. What do we know about multiplicities of odd numbers? This one has a 1 for each one of these, and 1 is an odd number. Now, is it going to cross, or is it going to touch at these 3 points? So using what we know about multiplicity, it indicates that whenever we have an odd multiplicity, it is going to cross at those 3 points. So our graph is going to look similar. So actually we already have enough to where we can just simply go ahead and connect the points, but it's always good to get as much information as you can so that you have more of an accurate sketch of the graph. So let's move on to step 4. In step 4, we're going to find the y-intercept, meaning we want to find a place where it touches the y-intercept, if any. So to do that, all you have to do is evaluate the function and find f of zeros. In other words, into the given function, remove all of the x's there and replace it with 0 to see what your output or your y value would be. So we're going to go ahead and evaluate this function for 0, and we can clearly see that everything cancels out there except that -3 in the back. So therefore, f of 0 equals -3. In terms of an ordered pair, it's going to touch the y-axis at 0 and down 3. So let's take a look at what that looks like. Go ahead and plot that point in addition to the points we already have. So we can see that it's going to go down to that 0, -3, and then come right back up through there. We actually have everything we need to go ahead and connect these points. But I want to go ahead, for the sake of going through the steps, and go ahead and look at steps 5. Okay, technically we already have an idea of what the sketch and the shape of the graph is going to look like. We really don't need to do 5 and 6. We can just connect it with what we have. But for the sake of going through the steps, I'm going to go ahead and go through 5 and 6. So starting with 5, use symmetry if applicable to help us draw the graph. We really don't need that because at the very beginning, recall, we looked at the leading coefficient, found it to be 1, which means that the graph was going to move from left to right in an upward motion, and that it was a third-degree polynomial, meaning an odd function. And recall that odd functions are symmetric with respect to the origin. So we already know that. We already know what the shape looks like. It's the S shape, and it's going to fall on the left and rise up on the right. And because of the leading coefficient, it's going to be moving from left to right in an upward motion. So moving on to 6. Now we can use our knowledge of turning points to help us to know how many turning points we can expect to see on our graph. So since this is a third-degree polynomial, n minus 1, that's going to be 3 minus 1, which means that this graph that we're going to sketch, we can expect it to have 2 turning points. So I'm going to go ahead and sketch the graph so we can go ahead and take a look at what it looks like. And here is our graph. And notice, yes, there are exactly 2 turning points on our graph. And so this is the other method, which is just simply using everything that you know about the characteristics of a polynomial function and using that information to help you graph until you're able to see a clear sketch of the graph. And there you have it, graphing a polynomial function. Okay, that's it for this lesson. Thank you for watching MVP Tutorials by your instructor, Dr. Speights. I hope you'll join me in the next lesson. Please feel free to like, share, and subscribe. Goodbye for now.